afternoon, everyone. I'll take your seats, and we will get started. So good afternoon. My name is Kim Strong, and I'm the chair of the Department of Physics here at the University of Toronto. It's my very great pleasure to welcome you to the 2023 Welsh Lectures in Physics, which I think is the 46th iteration. On this beautiful spring day, we've been enjoying the lovely weather. I'd like to start my remarks with the U of T Statement of Acknowledgement of Traditional Land. I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still a home to many Indigenous people from across Turtle Island, and we're very grateful to have the opportunity to work on this land and to gather together for events like this one. It's wonderful to be holding the Welsh Lectures in person this year, fully in person, after having kind of a partial return last year, one speaker in person, one online. And then in, of course, 2020 we had to cancel, 2021 we moved them online. So this is really my first set of fully in-person Welsh Lectures. So it's wonderful to be here and to see this great turnout. We're also very happy to be hosting the lunch. I hope some of you went to that. And then the reception after the lectures today, as well as a dinner for some people tomorrow evening. So I hope you can certainly attend the reception after today's lectures. So the Welsh Lectures, for those of you who don't know, are named in honor of Harry Welsh, who was both a distinguished molecular spectroscopist and chair of the Department of Physics from 1962 to 1968. Which is a period of tremendous growth in the Department of Physics. His association with U of T spanned more than 5 decades, from his enrollment in our undergraduate math and physics program in 1926, at the age of 16, to his retirement in 1978. So that's, I think, what, 52 years? Along the way, he supervised 65 PhD students, and his tenure as chair was marked by the introduction of research groups in theoretical, atmospheric, and high-energy physics, and the completion of our beloved McLennan Physics Building. Over the course of his 5 decades with the department, he saw it grow from 6 faculty and 12 PhD students in 1930 to 60 faculty and 150 graduate students, following the huge expansion in the 1960s and 1970s, in which the department began to resemble the one that we have today. In 1975, on the occasion of Professor Welsh's 65th birthday, the Welsh Lectures were established, and they've since become the major public event in the life of our physics department. The Welsh Lectures give us the opportunity to showcase to the broader community some of the most exciting aspects of current research in physics. Each year, we invite 2 physicists to speak who are known both for their extraordinary contributions in their field and for their skill in communicating the excitement of that work to a broad audience. This year, we're very fortunate to have as our speakers Professor Marcia Rieke from the Steward Observatory of the University of Arizona and Dr. Omar Hurricane from the Lawrence Livermore National Laboratory in California. While today's speakers work in very different areas of physics, each of them is at the forefront of their field, as you'll hear about today and tomorrow. Professor Rieke is the principal investigator for the near-infrared camera on the James Webb telescope, and her research interests include infrared observations of the center of our Milky Way galaxy and other galactic nuclei, and observations of the infrared sky at very faint levels, enabling us to study distant galaxies. Dr. Hurricane is chief scientist for the Inertial Confinement Fusion Program at Lawrence Livermore, and he's a plasma physicist working on inertial confinement fusion efforts conducted at the National Ignition Facility, which is the world's premier research facility for laser-induced fusion. I'm delighted that both of these speakers have agreed to join us to tell us about their very groundbreaking work, particularly over the last year. Both speakers remind us that science is a social endeavor. They're working on 2 enormous public efforts that are publicly funded. We're delighted to have a public portion of the Welsh Lectures as a way to make this astounding science more publicly accessible, and with time for Q&A afterwards. Where one talk is about the most ancient and most distant stars, the other is about a tiny synthetic star burning from the same energy process, and perhaps the most recent star to be born, as you will be hearing. This This year, the Welsh lectures are taking part over 2 days. So this afternoon, the speakers will be delivering the public lectures, and tomorrow they'll give a somewhat more specialized lecture on the current research, but everyone's welcome to attend all 4 lectures if you wish. And then, as I mentioned, there'll be the public reception following today's lectures held in the main lounge of the Faculty Club, which is at 41 Wilcox Street, just kind of over, a little bit north of here. So everyone's invited to attend the reception. Before we start the first lecture, I'd like to take this opportunity to thank the members of the 2023 Welsh Lectures Committee for all the work that they have done to bring these lectures to us this year. These are Committee Chair Robin Marchbanks and Professors Dick Bond, Youngjun Kim, Dick Pelletier, and Zan Su. So thank you to all of you for recruiting our speakers who are here today. I'd also like to thank the department staff who've helped with the organization, particularly Helen Iyer, who's provided much of the logistical support, as well as Eva Chung for graphics, especially our wonderful Welsh poster, Julian Kamandian for web pages and the departmental wall monitors, Supreet Randawa for all our social media outreach and publicity, Armin Mulkey for many additional ideas and solutions, and Pi Santiago and Tag Hearn who are helping out with the AV today. And so now I'd like to invite Professor Robin Marchbanks to introduce our first speaker. Over to you, Robin.
Good afternoon. Thank you, Kim. Today we have Peter Martin and Jim Davis to introduce our speakers. And I hope I don't step in any of the things that they were planning to say in their own introductions, but let me say a few things about how the committee came to ask each of our speakers today. Marcia Rieke isn't only the principal investigator of the NIRCam for James Webb, which has been a long time in the making, but a recent part of her whole career arc. Along with Judith Piper from Rochester, whom I knew slightly from all-night stargazing with her graduate students, these are the 2 women who quite substantially founded infrared astronomy, observational astronomy. The work that comes to fruition in James Webb Space Telescope is work that began with their efforts to even invent the devices that could be capable of forming images in the infrared, starting with a single pixel detector that they would scan across to form an image, and then the big thrill of a 32 by 32-bit imaging detector in the infrared. This is whole work. This is science that had a goal, working from the very creation of the necessary capability all the way through to the amazing images of the earliest times of what we know as existence itself. As for Judith Piper, she died February 21st, 2022, before the first public images were released. She's remembered especially for mentorship to many continuing scientists in the field. Dr. Omar Hurricane has been working in plasma physics for his whole career, but the goal of laser-driven fusion has taken thousands of people's careers since the time shortly after the invention of the laser. Based on my perspective, doing direct drive laser fusion for about a decade, starting in the late 1970s as a summer student, I think there hasn't been so much a single big trick or discovery. I think that for folks doing this work, it's been like running across the flat prairie, maybe in Nebraska, seeing from 100 miles away the town you want to get to, every day knowing that you must be closer, but not every day feeling that you're making any progress. And then one day you get there. Everyone who's watched Survivor on television knows the fire-making competition. Most of the time and effort goes into spluttering efforts to get a flame going. After that, it's about stacking the wood, assembling the fuel. Once you can make a thing work at all, making it work better is different. So this international news from the National Ignition Facility changes the picture meaningfully. On behalf of the Welsh Lectures Committee, the Department of Physics, and the University of Toronto, our sincere thanks to both our speakers, who have come a long way from home amid their perpetually busy schedules to bring us their stories of fresh science, stories they've been pursuing for many years. Thank you.
Good afternoon. Thanks for coming out. I'm Peter Martin, most famous for being brother of John Martin in your department. You're here not to listen to me, but in anticipation of a great lecture on the James Webb Space Telescope. by an amazing person, Professor Marcia Rieke. She's the holder of the Dr. Elizabeth Romer Endowed Chair at the Steward Observatory, University of Arizona in Tucson. Now, the organizers have written out her bio here for you to go through. So I won't recite it for you, but I will make my own remarks from my privilege of having collaborated with Marsha over the years. Marsha, as you've heard, is one of the handful of people responsible for the success of this most complicated space observatory. You can read about that again on web pages and web pages. I encourage you to do it because it's a very interesting history. And you'll see from the lecture why she was invited and why we're honored to have her here. So I want to say just two things. The first is that many roads to infrared detector arrays lead through Arizona. Not Route 66, but other roads. And there's quite a history over 50 years. Marsha is an entrepreneur whose skills and determination and leadership have put her in the thick of it. I first met Marsha in the late 1970s in the pioneering era of 1-pixel detectors. It's hard to believe that that's how it all started. And those were on ground-based telescopes. Marsha's interests were expanding into infrared observations of the center of our galaxy, out to other galactic nuclei, and then on to fainter and fainter galaxies in the distant and so younger universe. And this required access to space. She was the deputy PI on the NICMOS, near-infrared camera and multi-object spectrometer for the Hubble Space Telescope, along with the development of the MIPS multiband imaging photometer for the Spitzer Space Telescope, which provided long wavelength coverage. She was also their outreach coordinator. And for the past more than 50 years, she's been the principal investigator of NIRCam. You see the logo up in the corner. She proposed that, and she developed it successfully for the James Webb Space Telescope. That's a monumental high-stakes responsibility because NIRCam is absolutely the essential instrument from alignment of the mirrors through the imaging science that it delivers. My second point follows. These are team efforts, depending on combining diverse efforts and talents, both in technology development and in the planning and executing the science. Marsha has an uncanny ability to bring out the best of the team through many challenges, and many challenges there were. One example that I've seen up close is balancing the interests within the science team that naturally arise from the great versatility of NIRCam to do such a wide range of science. Initially, this included star formation in our galaxy, all the way to detection and characterization of the most distant galaxies ever seen or ever to be seen. But as the project developed over the years, the study of the rapidly developing field of exoplanets using coronagraphy was added to the technical and scientific mix. And then grisms for low-resolution spectra and extra specialized elements for wavefront sensing and telescope alignment of the mirror. Those too were added to NIRCam's portfolio. This evolving complexity could not have been achieved without Marsha's deep knowledge, trusted leadership, and firm hand on the tiller, providing a working environment that was inclusive, success-oriented, and very productive. Not only that, NIRCam has had a very effective STEM outreach program in collaboration with the Girl Guides of America. My third and last point is a big, warm welcome. We look forward to your talks.
Thank you very much, Peter. And as you may have guessed from some of his vignettes there, Peter is a member of the NIRCam team, so he knew some of this inside stuff. Okay, before I get into the real talk, I should mention that although I'm not giving a talk on the University of Arizona campus, we too recognize that the Tohono O'odham people of southern Arizona used to own the land that the University of Arizona is built on, as well as some of the mountaintops where our telescopes are located. And we also like to acknowledge with gratitude our ability to use that land in those mountaintops. So let me start. You'll notice I'm wearing some of my own data. Don't always get that chance. But let me explain a little bit about this picture. So this was one of the ones that we called an early release observation that was taken to highlight the telescope's and instruments' capabilities. And I'll show a few more of these. And one thing to remember when you look at this image, it is not an image that you can see looking like this with your eye. The Webb telescope works at infrared wavelengths, so its very shortest wavelength is the deepest red human eyes can see, and all the rest is invisible to your eye. And so an image like this is constructed by taking a number of images through different filters using NIRCam, and then assigning a color to each one of those filters. And that color assignment is done as a group exercise between someone who has artistic talent at Space Telescope Science Institute sitting next to an astronomer who has an idea of what some of the scientific content of the image is. And they work together to make something that is visually appealing and also reveals some of the science. So here, this bottom part, which looks like mountains or dirt in some sense, is an area where there is in fact a lot of interstellar material, dust and gas that obscures much of what would be seen behind, and so it shows up best in some of the longer wavelength filters. This area on the top, which looks suspiciously like sky, is actually a region where the newly formed hot stars have blown away most of this interstellar material, and you can see more clearly through space. And so I should also mention that this little object here that's in yellow is actually a blob of gas shot out from a forming star, a protostar. And it has this shape because it's got a shock wave due to crashing into this other much cooler material. And the emission that you're seeing here is from molecular hydrogen in the shocked region. So there's a lot of astronomy actually in this picture, and in fact some people have already written papers based on what you see here, even though it was contrived to be visually interesting. And I think part of the reason that the Webb mission has garnered so much good press is that if you think about, we launched in near the end of 2021, and the world was just coming out of the pandemic era. And I think this sentiment is well spoken, that we got a lot of press because we were some good news for a change, and interesting good news. So we launched on Christmas morning. You had to get up at 5 a.m. in Arizona, not quite so early here. And you'll notice it says ESA and Ariane. We were launched on an Ariane space rocket provided by the European Space Agency. And I have to tell you, there were some in American aerospace companies that were just appalled that this was being done. But if you go back and look particularly in the early 2000s when we were choosing how to configure the mission, the Ariane 5 rocket was the only one capable of lifting this mass that we projected for the telescope. It was also the most reliable. And SpaceX didn't exist yet. And I have to say, launching on the most reliable rocket is a good thing. And so we launched. It was an absolutely perfect launch. And then as time, about 2 weeks went by, we went from this folded up configuration to the fully deployed mission with the telescope with its mirror segments laid out to catch starlight, and the sun shield deployed to keep the sunlight, earthlight, moonlight off the telescope so we would get adequately cold. And this gives a little schematic of how this works with, you can see that by being out at the second Lagrange point, the sun shield blocks all the local hot stuff. So it's a very convenient place. And it's also a good place to be from the standpoint of telemetering data back to the Earth, because the second Lagrange point is this nice special semi-stable gravitational point where the mission and the Earth go around the sun at basically the same rate, so we stay in this same relative orientation, and so you can point your telemetry antenna in basically the same direction all the time, which is quite convenient. And of course, there was lots of press about how many single point failures there were in this mission, and this is where this quote originated from the NASA administrator for science, that there was a lot of worry about what could go wrong. Luckily, nothing went wrong, and it was quite remarkable. So to give you a visual sense of why astronomers want to observe at different wavelengths, I think many people now remember this Hubble Space Telescope picture of another star-forming region, sometimes dubbed the Pillars of Creation. And you notice in the background that there are not very many stars, which is because there's interstellar material that blocks them out, not as strongly as these discrete clouds, but pretty strongly. Now we move to the Webb telescope in NIRCam, and you can see many, many, many stars that poke through this collection of dust. And if you look at this region, for example, here's a whole little collection of stars that you don't see in visible light at all. So even though you've only moved out about a factor of 5 in wavelength, you get quite a different view. And then we go one more step. Webb includes a mid-infrared instrument that works all the way out to, depending on what units you like, 28 microns or 28,000 nanometers. And you can see that the structures bear some resemblance, of course, but this is now the emission from the dust that is blocking out the starlight over here. And so you might ask, why is it important to go to space? And Peter hinted at that in the introduction. So this guy who is holding a match in front of a blast furnace, you may be able to pick out the match, but it's not that easy. And the background here relative to the match is somewhat like the background you get on a ground-based telescope in the infrared from the heat of the telescope and the heat of the atmosphere and the Earth's surroundings. If you can get rid of that, bingo, it's much easier to see the match, and you do that by cooling the surroundings. And of course, you can't do that on the ground because water, vapor, atmosphere, everything would just condense out on the telescope. So space is very important for doing infrared astronomy, beyond the fact that the atmosphere absorbs a lot of the infrared. So we needed a folding up telescope because we wanted a 6.5 meter mirror, diameter mirror, to be able to detect the first galaxies to form. That was one of the original goals. And the science working group drew a line in the sand at 6.5 meters, that if we went smaller, we didn't feel confident that we would detect them. And originally the mission was slated to be 8 meters, but that was changed relatively quickly because we realized we couldn't make enough mirror segments fast enough to launch in a reasonable amount of time. So we shrank to 6.5, but that was the limit. So nothing fits inside the nose cone unless you fold it up. And of course that presented a whole series of challenges to the mission, but which the engineers successfully came up with the way to do it. And this mission had quite a trip. Everything got assembled, everything but the spacecraft and sunshield got assembled in Goddard, and we tested it there. We then put it into an airplane and took it to a test chamber at Johnson Space Flight Center in Houston, and the chamber that we used was originally designed for testing the lunar rover, so it gives you a sense that it was old and big and needed a lot of refurbishment. The other fun thing about this particular cryogenic test was that Hurricane Harvey hit Houston while we were there. Telescope was safe because it was in a big vacuum chamber, but the people weren't safe. None of us got hurt, but it was a little bit trying to drive through 1.5 feet of water to go from the hotel to the test facility. When that was done, where we tested the telescope mirrors with the instruments, we then went to Northrop Grumman's facility near the Los Angeles airport, got the spacecraft and sunshield mated, and some more tests, all warm tests though, because there was no chamber big enough anymore to test it cold. And we got put on a boat and ended up in French Guiana, where the Ariane Space Company has their launch facility. This is what it looked like going into the airplane. We had a portable clean room that held everything to keep the optics good. And now we're at Northrop Grumman in Los Angeles, and this is where the telescope is being mated to the spacecraft and sunshield. You can see some cables which had to be connected right to get the signals out of the instruments and down into the telemetry systems that reside underneath this sunshield. So they are critical for command, control, data flow. This is what it looked like just before shipping to French Guiana. You can see it all nicely folded up. And you can tell from the size of the people that this was a big piece of equipment. And it weighed over 5,000 kilograms. There's the boat that was used to take it to French Guiana. It went through the Panama Canal. And you might ask, why didn't we just keep using the airplane rather than go on a boat? Well, it turns out that French Guiana does not have an airport capable of having a C-5 airplane land. And the nearest such airport, there were no good roads, so we went by boat, which is what the European Space Agency usually does with their equipment. And this shows the launch complex. If I hadn't put a name on it, you might have just thought, oh, it's any other launch complex. It looks quite similar to Cape Canaveral. There's nothing particularly unique about it except that it's in a good location. Here in this picture, you can see some of the many, many places that contributed to making parts for Webb. And there were a total of 17 different countries that contributed. This was very much an international project. So it involved 3 space agencies, NASA, CSA, the Canadian Space Agency, and ESA, the European Space Agency, and then a lot of other countries that contributed as well. And this is, in addition to being some good news after COVID, it's also a demonstration that people can still come together, a very diverse group of people, and achieve something magnificent. And I think we shouldn't lose sight of that human aspect of this. And I wanted to mention that since we're in Canada, that the Canadian Space Agency played a role in this mission from the very beginning, from the earliest days of what we called the Ad Hoc Science Working Group. And that's partly because this mission does science that Canadian astronomers were interested in doing. And so they wanted to participate and contribute, and they certainly have. And the 2 main contributions are the fine guidance sensor, which the role of the fine guidance sensor is to lock on to a star, centroid it, And if the telescope jitters a little bit because of the solar wind or whatever, it sends an error signal to a fine steering mirror and keeps the image perfectly aligned. And this has worked so well that any little jitter in the telescope motion contributes nothing in the end to the final budget for the optical quality. The FGS has worked just magnificently. And the Canadians also built another instrument called the Near-Infrared Imager and Slitless Spectrograph. And I'll talk more about this later, but this is a spectrum produced by NIRISS of an exoplanet, demonstrating that that exoplanet has water in its atmosphere. And several of the features in NIRISS are very good for studying exoplanets. And this is just a picture showing the delivery to Goddard Space Flight Center, where the instruments were gathered together. And this is a picture of the instrument itself. The FGS and the NIRISS, were mounted on a single optical bench. So after the telescope got launched and deployed, there was a very long, what we call, commissioning process. And when you launch something and it gets up in space, it's not immediately ready to take data. And particularly not this mission, because we had deployed the mirrors, but we had to line them up so that they would act like a single smooth mirror instead of 18 individual segments. And then we had to, once that was done, we also had to provide an initial calibration and checkout of the instruments. So the first step, once NIRCam got cold enough, was to find which direction each of the 18 mirror segments were pointing. And each one acts like a sort of an individual telescope. And the engineers predicted that when we got in space, the launch vibrations and uncertainties in the deployments would mean that it was potentially the case that the 18 mirror image star images would be spread over an area nearly the area of the full moon. And that was covered then, the likely area, with a grid of NIRCam pointings where we would find these not very well tuned up images. Well, the first indication we had that we had a very nice conservative set of engineers was where we actually found these images. They were found in a much smaller area, and I think we all agree that having engineers that are conservative is a good idea, because then you feel confident getting on an airplane. But it meant that all through this process, things worked better than predicted because the engineers are conservative. Bless their hearts. Okay, so what did that set of images look more like? This was the mosaic of the first images taken. NIRCam was at 100 degrees Kelvin, so much warmer than the final operating temperature. If you count them, there are 18. Those who have pretty good eyes can see that these are labeled with ABC and various collections of numbers. ABC refers to the 3 different optical prescriptions that the various segments were polished to, because depending on where the segment was in the mirror plane, they got a little bit different optical prescription. So we had to go from this scattered set of images to a diffraction-limited telescope. And this got some press. This was called the selfie. It looks pretty grotty because it was taken again at 100 degrees Kelvin, much warmer than we were intending on using NIRCam, and so it's a bit out of focus. And the particular one of those 18 images that we were pointing at lit up its corresponding segment. And so later, when we would take these after alignment, all of them would be lit up because the star light was then had been stacked up and aligned. So this shows now where we took the 18 images and arrayed them in a convenient pattern for relating what we saw to the commands that we had sent up. And if you watch, you'll see that some of these are clearly look out of focus, And if you're into optics, you may just take a look at this and realize that the predominant problem is astigmatism. And the fact that we saw focus and astigmatism and virtually no other optical aberrations, the wavefront sensing team was ecstatic, because these are the two aberrations that the control actuators on the back of each mirror segment, what they could take care of. They could, astigmatism is tip tilt, there was tip tilt control, focus meant moving the whole segment up or down. So all we had to do was figure out how much to move each segment to make it perfect. And you can see from this little, you can see how it goes from bad to good. So we got the first step. We got the segments into pretty close to final position. But of course, we don't want 18 individual images of the sky. That'd make a mess. We want them to be one single diffraction limited image. So let's see what we did. There it is, after we went through various steps to bring the 18 images on top of each other and do what we call phase them up. We came up with this lovely telescope evaluation image, and this is indeed diffraction limited. It beat the original requirements by about a factor of 3, and that has a very nice benefit to the science. We can do some things that we hadn't anticipated. And you may notice some things in the background here. Those are not flaws. Those are objects in the background beyond this star. And one of the wavefront sensing team members went and gathered up all of those, what look like annoyances in the background. They're actually a whole bunch of different galaxies that just happen to be in the background, showing the power of this telescope to study galaxies, which of course is one of the reasons we built it. And you can see many different shapes here. These are not anything like the most distant galaxies, but some of these, we're seeing them as they were at about half the current age of the universe. So they're pretty far away. Some of you may remember the press making a deal out of the fact that a micrometeoroid hit the telescope. We had just finished getting it beautifully aligned, and there was this little, metaphorically, ding. And it's estimated that what caused this hit, which actually made a little deformation of one of the mirror segments, was about the size, about a 1 micron size piece of sand, but moving at 60 kilometers per second, so it had a lot of energy. And it actually deformed the mirror. This, by the way, is the shadow of one of the struts that holds up the secondary mirror. And we readjusted things to minimize the impact of this. And the impact, so to speak, of the impact was pretty small. And we have not seen in the years since that happened, we've not seen any more of that size. There are other smaller ones that hit that don't make any deformation, but are noted because they cause a little vibration throughout the telescope structure. And those tiny hits are occurring at about the rate that people from Marshall Space Flight Center who keep track of space debris would have predicted. And then, once we had it all lined up, and we checked out the instruments, made certain that they all changed their filters and their detectors worked and so on, science could begin. And so this is a collage of some of the early release observations. And I'll go through what some of this was all about. One of the early release observations was of a dying star, a star that was a red giant, blew off its outer layers as part of its evolution, and a white dwarf remained. And you only see the white dwarf here in the longer wavelength image because it's still obscured by some of the dust that got formed from this action of throwing off the layers. And you can see in both of these evidence for the remnants of when this star was pulsating, getting bigger and smaller and throwing off its outermost layers. And analysis of all these kinds of structures will take a long time to understand all of the physics in getting those gas layers off the outer parts of the star. There was another thing that was obvious in this picture. I thought this was some kind of weird scratch. No, it's an edge-on galaxy. And once again, we see JWST images being so good at finding galaxies. And so we say they're photobombing almost every image. And there was an episode last summer where a French scientist tried to play a joke, and he cut off a piece of chorizo, took a picture of it, and put it out on Twitter, and he said, this is JWST looking at an exoplanet, a planet around another star. And it took almost no time for the Twitterverse to say, fake, because there were no galaxies in the background. To me, it looked like a piece of chorizo from the get-go, but we'll... All right, so here's a little sequence that will show you how a relatively nearby galaxy changes its appearance as we step through the JWST instruments. But first, this is what the Hubble Space Telescope showed for this galaxy. And you can see some reddish-brown stuff that's where dust is absorbing the starlight being emitted from that galaxy. Now, we go at 4 times longer wavelength, and you see all that dust stuff disappears because NIRCam can see through the dust. It doesn't obscure the infrared photons. And it's a little bit hard to discern, but this is a pretty good projector. You can just begin to see that this galaxy, we're actually seeing the individual stars, even though it's 36 million light years away. And we had not projected or promised being able to see individual stars at this distance. But because the image quality is this factor of 3 better, we can see stuff that we hadn't planned on seeing. And I'm sure that when we peruse the list of recently approved proposals, we'll see ones from people wanting to study individual stars in nearby galaxies for comparison to the Milky Way. And now, if we go one more factor of 4, that's what that galaxy looks like in the mid-infrared to the MIRI instrument. And you see it looks totally different because now we are seeing PAHs, polyaromatic hydrocarbons, which are a kind of dust grain that occurs out in space. You can also collect some from the soot of your car exhaust if you have a gasoline-burning car. And these outline regions that we call photodissociation regions, which not only contain this kind of dust, but also contain the hot stars that can excite transitions in them, and you can see them this way. So one of my projects that I've gotten most interested in now, because with arrays, looking for the most distant galaxies is much more fun than when I had to go and look with a single pixel. And so this is a very schematic version of the universe. And so here we are sitting today at an age of the universe at about 13.7 billion years. And what we want to do is go back and see what's happening as close as we can to the time after the Big Bang. There is, of course, a limit around 300 to 400,000 years, because until that plasma cooled enough and the hydrogen, protons, and electrons recombined to form neutral hydrogen, light could not propagate freely throughout the universe. And so that kind of sets a limit to how far back we can go at visible light wavelengths. The cosmic microwave background comes from this era when the protons and electrons combine to become neutral atoms. And so somewhere in here, the very first galaxies formed with clouds of gas that collapsed, fragmented into stars, and became objects that we could see. And we will now see momentarily how close we've gotten. Z of 15 was sort of one guess. But let's see. You notice that there's some ages attached here. And we'd like to see from 400,000 years after the Big Bang to later times. When do those stars start radiating? When can we see them? What are the gravitational processes? What role is dark matter playing in all of this? And so on. So for those that are not used to astronomer speak and how we think about things, it takes light a long time to go from here to there. We don't usually think about that, but it certainly does. And so it takes 8 minutes for the light to come to us from the sun. So if the sun turns off, we won't know for 8 minutes. But we're not going to worry about that. Not likely to happen for 5 billion years. The nearest star takes just under 4.5 years for the light to get to us. That's a clue why it's hard to go visit other stars. And then it takes light billions of years potentially to reach us from another galaxy. So if we can measure by some means the distance to a galaxy, then we can know how old the galaxy was when we were looking at it by just taking the age of the universe and subtracting this light travel time, and the difference is what the age of that object is. So when we look at the most distant galaxy that we can find, it takes light 13 plus billion years to get to us, and that galaxy might only be a few 100 million years old, so it's very young, and the light travel time is very long. And it's quite easy, because of the way the universe works, to measure the distance to these objects. Because the universe is expanding, therefore things throughout the universe appear to be moving away from us. That means their spectral lines are shifted to the red because everyone's moving away from us. And so if we measure the amount of that redshift, then we have the distance to the galaxy. And for those that are proficient at mathematics, you can compute as a function of what we measure as the redshift in a spectral line, you can calculate what the look-back time is. And so if we estimate the redshift, we've got the distance, and therefore we've got the age of the galaxy that we're looking at. So that's the way the game works. And here schematically shows 3 galaxies at 3 different redshifts, 10, 11, 12. And for this top one, you can see a Lyman alpha emission line and some others. And at redshift 11, that moves toward redder wavelengths. At redshift 12, it moves even further. And you can see that the age of this galaxy is 480 million years. And down here by redshift 12, it's already dropped to 370 million years. So this is how we correlate distance with age. And this is a blink between 2 images, a JWST image and a Hubble image. And the Hubble image was taken some time ago. The JWST image was one of these early release observations, and it's this one that looks a little clearer. This was part of the early release observation set, and it was one that President Biden wanted to show off. And I'll tell you, people at NASA headquarters were really shocked that the US president wanted to release some science data. We were really happy. I mean, that hardly ever happens. All right. So if we look at this carefully, one thing you'll notice is that there are some arcs, and this collection of galaxies here is a cluster with a lot of mass, and it does gravitational lensing, so those arcs are gravitationally lensed galaxies way behind this galaxy cluster in the foreground. But what you find quite interesting is, for example, look at this spot. The Hubble image, there's nothing, and there's a very red galaxy in the Webb image. And that is kind of a graphic demonstration of why astronomers who wanted to study distant galaxies wanted to build something that would go to redder wavelengths than Hubble. And here's that JWST image again with 4 galaxies chosen for study with near-infrared spectrograph on Webb, and you can see a pair of lines here colored red and blue. Red is hydrogen and blue is a pair of oxygen lines at about 5,000 angstroms in the rest frame. And you can see as we go to more and more distant galaxies, these get shifted more and more to the red. And the age of the galaxy we're seeing the look-back time here of 11 billion years down to a look-back time of 13 billion years. And so the ages go from 13.7 minus 11 to 13.7 minus 13, so only 700 million years after the Big Bang. And I'm part of a team called JADES, the JWST Advanced Deep Extragalactic Survey. I don't know how many, I know physicists like to make up names for things, astronomers do too. And some of them are a bit forced, but we won't go there. So this is a sample of some of our imaging data. And then what we do is we take some imaging data, we go through a process of looking at the photometry in a variety of filters over the whole 0.6 micron to 5 micron range and pick out what we think are the most interesting objects to look at. And interesting can come in a variety of flavors. It might be a distant X-ray galaxy or radio source, or it might be something that we judge to be the most distant galaxy. That's one of the things that propels a lot of people. And you pick out and lay down some slits. The NIRSPEC instrument on Webb can observe up to about 200 objects at once. And the slit selection is fully programmable. And so we can do multi-object spectroscopy, which helps a lot because these exposures are 100,000 seconds. So you can't do this one at a time and build up any population statistics. This shows a sample of some NIRCam imaging. And you can see that it's completely gone at the shortest wavelength. And that's because the universe is full of hydrogen still. And any energy emitted by the object you're studying, shortward of 1216 angstroms, where that's the ground state transition of hydrogen, Lyman alpha, anything more energetic than that gets absorbed by the hydrogen. And so the universe becomes essentially blank. And that's another one of the reasons we had to build Webb, because Hubble stops right about here. And so it would never see this particular object because of that hydrogen absorption. Just to give you a graphic that shows, again, this is a Hubble Deep Survey image, and this galaxy is blown up here. There's that same galaxy in the Webb data, and you can get a very clear visual impression of how much better the spatial resolution is with Webb. We did a project where we had made this big mosaic, sorted through, and by a little bit of sleight of hand, we found 4 objects that we thought were very high redshift. But by a somewhat fortuitous set of circumstances, we were able to sneak them into our first NIRSPEC spectroscopy exposure. We hadn't planned on doing this, but we got things turned around so fast that we could do this. And here is one of those objects, and what you see here is the actual NIRCam data for something which in this suite of 4 was not the most distant, but pretty far, much further than anything Hubble had ever seen. The center row is a model of these objects. These are the residuals. This shows a plot of the photometry done 2 different ways, and a possible fit to the spectrum. And then we actually, since we had 4 of these objects, we got spectra of 4 sources, and the red line shows this Lyman break, and these don't look very pretty, but they all confirm that our selection method for these very distant objects was correct. And so this particular object here is the most distant galaxy that's been spectroscopically confirmed. We're pretty sure that our data set has more distant ones, but we haven't gotten spectra of very many things yet. Let me finish off by touching on a couple of the other areas where Webb is making a contribution. And there are several ways one can look at exoplanets. One way is to do direct imaging, which Webb is equipped to do. The other way is to do what we call transit studies, where the alignment is such that the planet crosses the face of its parent star. And if you difference the signal with the planet there and not there, you can learn about what wavelengths get absorbed by the planet's atmosphere. And this is that spectrum that I showed earlier from the Canadian NIRISS instrument. And you can see very clearly water. And as we've gone along, it looks like water is pretty easy to find in exoplanets. So water is probably not a biomarker per se. It may be necessary, but not sufficient for declaring a planet being capable of having life. This is now our other near-infrared instrument, NIRSpec. And this is a spectrum now that covers its entire sensitivity range. And it finds carbon dioxide, sees some more water, there's some carbon monoxide. And this feature here, which was not expected, sulfur dioxide, was an unexpected discovery, and that has some of the astrochemists quite excited because this is a disequilibrium material. It's not, something has to be going on to replenish it. And I just blew up the carbon dioxide feature because I find it amazing that we can study greenhouse gas on an exoplanet, and we're going to be doing more of that. Now let me also mention another kind of transit observation. There's a set of planets around the star, TRAPPIST-1. You can tell that TRAPPIST was part of a Belgium sky survey, and they named their things after beers sometimes. And the Spitzer Space Telescope observed the transits and deduced that there was a whole family of exoplanets around this star. And, whoops, wrong way. This whole family would be inside the orbit of Mercury, so you would think hopeless for life, but not so, because you notice this TRAPPIST star is shown as kind of a dim red star, and so the habitable zone where water might be liquid is much closer to the star. And so it's thought that some of these could potentially be Earth-like. It's known that their sizes are somewhat like Earth. So what was found, only the nearest innermost TRAPPIST planet has been observed so far by Webb. And this is now a different kind of observation. This is one where instead of taking spectra, you monitor it with the mid-infrared instrument and you look at the difference in the light emission between star plus planet and star alone so that you can subtract out and get the emission from the planet, which then gives you an idea of its temperature. And so here's a thermometer, and this is the temperature that was measured for TRAPPIST-1b. And if you go through the math, it's at the equilibrium temperature for a dark rock at its distance from its parent star. No atmosphere at all. So much for that one, but there are still 5 more to go, and they will get observed in due course, and maybe one of them will prove to be more interesting, and maybe eventually we'll find a spectrum that looks like this. This is now presented in inverted form from those spectra, where in principle, if we can find an Earth-like planet that has an atmosphere, we could measure something like this that would tell us that this planet, this exoplanet, has an atmosphere like Earth's. Not there yet. There have been some solar system targets. You can see This is a very nice picture of Neptune and its rings, the very best picture of its rings ever seen, some of its little moons. Nice picture of Jupiter. And if you go look at a bigger scale, it's a little bit hard to see here, but Jupiter has a ring which was known from satellite missions, and it has aurora, so it's got lots of interesting things going on. And this is by far the best picture of Uranus's rings. So if you want to study rings in the solar system, which are basically collections of dust particles, again, Webb is a great tool for looking at dust. And so I'll just conclude by saying Webb is working fabulously. Stay tuned, much more good stuff to come. Thanks for listening. So if we have time for some questions, I think Peter will moderate those.
Is there a mic? Yes, there are mics here. Or you can speak very loudly.
If you speak loudly, I'll repeat your question.
Like you said, we can't trust what's on social media or Twitter. Social media is now claiming that JWST is making discoveries which are bringing Big Bang cosmology into question. Is any of that actually correct? Are any discoveries being made which would cause us to question Big Bang cosmology?
Yes. This question about whether or not Webb is going to overturn either Big Bang cosmology or what we call lambda CM, the dark matter theory that prevails. These claims are based on the fact that if you take the numbers of very bright high redshift galaxies at face value, analyze them in the context of how local stars form, then you think these objects are very massive because they're quite bright. But we don't have an independent way to measure the mass, where you do it by taking how much light they produce and convert that to mass by a recipe that includes the distribution of how stars form as a function of mass nearby. That prescription, which astronomers call the initial mass function, is almost certainly wrong at the very high redshifts because of a very simple fact. Locally, the cosmic microwave background has a temperature of 3 degrees above absolute zero. When you go to these most distant galaxies, let's just say redshift of 10 to make the math easy, then the temperature of that microwave background at that point is 10 plus 1 times warmer. In other words, it would be 33 degrees Kelvin, and what we call the Jeans mass, that is the mass that can collapse to form a star, will be correspondingly larger. And if this prescription of how many of each type of star forms gets weighted toward bright stars, you can get a lot more light without having nearly as much mass as if it were done locally. And those low mass stars don't have an observational signature beyond their gravity, but we don't have an independent way to measure the gravity in these distant galaxies. So I think when all is said and done, we may not change cosmology, but the jury, to be fair, is still somewhat out on this question.
Could you summarize what the main survey efforts by JWST are, and roughly what time scale for those of us who feel
Okay, there was one set of early release science that was a deep survey, not quite as deep as what my team has done, but those data are already available, but they don't have as good short wavelength coverage, so it's a little bit hard to do good photometric redshifts. There are 2 other surveys that did much bigger areas on the sky. Those data are also all public, but again, they don't have enough filters to do a good job on the photometric redshifts. And our own deep survey, which has the best selection of filters because we put half of my team's time into the survey, We're going to release the first part of it in June before our proprietary period ends. And when we release the images, we'll release mosaics and catalogs, and so people can really go start having at it.
Are there any plans to do any kind of upgrades to the Webb telescope? I've heard about things like maybe a star shade or something. Is it really inaccessible, or?
Well, it's certainly inaccessible to astronauts right now, so we won't do that. And the star shade idea was investigated for a little while, but Webb is quite a big telescope, and so it needs a very big star shade. And I think there was a plausible star shade proposed for Roman, which is much smaller, but the Webb one kind of died because no one was sure that its shape could be maintained to sufficient accuracy. I think probably the pointing could be handled, but the big problem with the pointing is that to move to a new target takes a very long time, and the estimates were that before the fuel ran out, maybe you'd get 10 targets, and that wasn't worth $1 billion in some people's estimation, even though it's a very nice way to do coronography.
Does JWST also do astroseismology?
It can. The same kind of observing mode that's used for transits, where you sample often, can be used for astroseismology. And I think there were some Cycle 1 proposals, but I don't actually know if they've gotten their data yet or not, but it can. In fact, for a single target like that, NIRCam can be read out at a rate of a few hundred hertz even, if for some reason you wanted to do that.
On the order of micrometeorites and stuff, what are the limitations if, say, for example, like is it in an area where there's particularly low chance of struck, and if it is struck, what do we do if it's pushed out of the line?
It's in just basically an average position. It's not like in either a place where there's none or where there's a collection, because the one that hit was actually what they called an erratic. It came from a very strange direction, so that there was nothing particular about the location. There are some precautions being taken, because if you have the mouth of the telescope facing in the direction you're moving, you're more likely to get a big hit than if it's tipped some other way. So there's kind of now a little bit of a zone of avoidance for pointing, but since you can still point you can get the whole sky anyway, it's not a big impediment. And there's a relaxation if you have a transit at a particular time. They'll let you point even if it's in this possibly not so good direction. But it's not thought that there's anything especially good or bad about the JWST orbit, just bad luck.
If it gets struck and it's spun or something of that nature, or damaged in some way, what happens then?
Well, like what happened this time was that the wavefront sensing guys analyzed the images and discovered that if they made slight adjustments to the position of that particular segment, they could minimize the problem. And worst case, it could be completely tipped so that it wouldn't contribute to the light at all, but we hope we don't have any like that.
The exoplanet observations, can you give us a sense of how far away can I do that? Is it strictly within our neighborhood? Can I see exoplanets in some astrophysically different regions of the different galaxy? Is there some rough feeling for it? As long as you can find them so that you know the ephemeris, and the star isn't too faint, if you can get enough photons, then you can look anywhere. And I think one of the targets was, I don't know, nearly 2,000 light years away. So it wasn't exactly the solar neighborhood. I wouldn't want to claim going really far, because you need to find them ahead of time, and that's not so easy.
Is it a list of things that
Remarkably, the technologies chosen have stood up pretty well, as have the projects. And in fact, the vendor that sold us these infrared arrays still sells them. So the main difference now is that you can, instead of buying 2K by 2K parts, you can get 4K by 4K parts. The mid-infrared detectors are much harder to get, and I'm not totally sure you could replace them right now, remarkably, because the company wasn't making enough money on astronomers to be worthwhile. I think in terms of would I have made NIRCam any different, I think one thing I might have wanted to think through is that we have some what are called GRISMs in our long wavelength channel, and their parameters were chosen to support wavefront sensing as a backup. We now know that there are so many high redshift galaxies that have strong emission lines. We might have configured those slightly differently to have a little bit bigger field of view, so to speak, because that's proving to be a very exciting strategy. But by and large, one might not have changed a whole lot, but I think that's because this was such a big leap that it's not out of date yet. And I should say the next missions that are being contemplated by our space agencies are ones focused on direct imaging of exoplanets, which is not Webb's forte because with 18 mirror segments, there's a fair bit of diffraction that's not nice and was kind of implicit in launching a folding up telescope. Now, whether one wants to cast one's lot with Elon Musk and be able to launch a monolithic big mirror, I'll let you younger folks decide that.
Given the success of Webb, should we be putting money into graphically telescopes?
Oh, absolutely, because they have different niches, different research strengths. Like the University of Arizona is collaborating with a number of other universities on what we call the Giant Magellan Telescope in Chile. And that telescope will have higher angular resolution, which is good for studying exoplanets, and also can support very large high-resolution spectrographs. The maximum resolution of any of the spectrometers on Webb is 2700, which to some people is barely a spectrometer, but to some of us that's pretty good. But if you wanted to do very detailed chemical abundance analyses of different stars at different positions in the Milky Way or whatever, the ground-based telescopes have a lot to contribute. Yes.
How successful are the parallel?
The parallel observations, by and large, have been very successful, and we're being able to get the same suite of filters so we can get the same high-quality photometric redshift data. The one thing bad that happened was that one time there was one of these, what they call optical shorts in NIRSpec, that caused it to make some extra light because of this electrical issue with one of the little slits. And that light showed up in NIRCam and made some funny ring structures that we still don't understand. But that's the only bad thing that's happened with the parallels. And it's really, really nice to double your coverage on the sky, basically for free, because you're taking data with the other instrument.
To follow up on Peter's question, are you limited in telemetry by how many of these parallel observations you can take?
Yes, in fact, that's why you can't run all the instruments at once. And NIRCam does not send down every readout of its detectors. It averages groups together. And so telemetry bandwidth is a real constraint. And so, for example, the transits, which tend to need a lot of high cadence data, are not done in parallel. You know, you don't do a parallel with those, for example. And so one of the metrics the Institute keeps track of is how much data per unit time is being generated by a particular configuration, and that is a limit.
Can I ask a follow-up contentious question? Given the value of these instruments, why don't you build another antenna on the ground?
Well, we could, but the problem also is that we, I guess we could just build another one on the ground, and I'd have to look at the power budget to see if we could be sending data down all the time. The other limitation, which is also related to not having enough ground stations, is simply that there's a solid state recorder that keeps the data until we can downlink it, and that can't be made any bigger, obviously. But if we could send data down all the time, then that wouldn't be an issue either. So go find your telecom friends and see who can.
Yeah, just a quick question. So you were talking about imaging and spectroscopic, taking the spectroscopic nature of the exoplanets around stars and stuff like passing in front of it and taking that spectral data. The question I have is, do we have the capability of actually imaging the exoplanets themselves, or is it because they're so close to their stars and it's difficult to actually make them out?
We actually, in some cases, do have the ability to image them directly, but not the ones that do the transits, because you need this edge-on alignment, tend to be close to the parent star, and I don't believe there's any case where we can image one of those directly. We image different ones that are further out, and there is a question of whether or not we might be able to get a spectrum of one of those somewhat further out ones, because some people are so fixated on Earth-like ones that won't help that question, but we could learn a lot by taking some direct spectroscopic data as well. There are a handful of cases where we might be able to do that.
Thank you. So this was a very expensive telescope. If we wanted to make an identical telescope now, nothing changed, and launch it, would you have an estimate how expensive that would be? 50% of what was spent already, or more than 50% or less?
I don't have an accurate estimate of that. One of the things, obviously we wouldn't have to redo the design because that's all in place, but most of the money went into assembly and test. And I'm afraid that would not change because you wouldn't want to launch something without testing, because even though you've got the design right now, you have to make certain that people assembled it correctly, which can't be 100% counted on. So, it might cost, just to make a guess based on how long it took us to do the different phases of the mission, it might cost 70 or 80% as much to launch a copy.
Thank you.
Mm-hmm. Yes, and spectra have been taken, and I don't recall that the imaging revealed anything particular about the spatial characteristic, but the imaging was done in filters that would isolate various ices. And so we're going to learn about the surface composition of those guys. And I think there might be a binary one that someone's going to look at too. And thanks for being a good audience.